You know, mathematics is often called the science of patterns, and you can think of juggling as the art of controlling patterns. A lot of the jugglers are mathematicians or computer scientists, have patterns, say, on every prime number throw, do something. Well, you're computing like mad and juggling, and it's a real kind of a mental as well as a physical challenge.
Where do you see combinatorics going in the near future?
Most mathematical statements are kind of beyond proof of human being in the following sense. Look at one of the more recent accomplishments, say the classification of finite simple groups. You can state the problem on a page. Could you ever find a proof in 100 pages, 1,000 pages? I don't know. When you're trying to prove something, you're kind of convinced it's going one way, but it's really going the other way. So I have a saying I always keep in mind. The main obstacle to progress is not ignorance, but the illusion of knowledge.
It sounds like you're even really rejecting the dichotomy between concreteness and structure, namely they're both present.
So I always had the belief that somehow mathematics, the probabilistic method, is very powerful. And it says, look, you just look at all possible graphs, for example, where you flip a coin, put an edge in or not, and with very high probability, something happens, okay? And then you can use this argument to show something must happen, because the bad things, there's just not enough of them. But you don't know how to get a good thing. You can't actually construct a good thing. And I always felt that constructive methods are really, eventually will dominate. But now I'm not so sure. Not so sure, you know? Not so sure. I mean, the fact that we're humans is really pretty limiting.
Well, Ron, where were you born? Where did you live as a child?
Well, I lived all over. I was born in California, kind of the middle of it, but then I moved to the Bay Area off and on, and it was during the war, and my folks worked in the shipyard, so we worked in Richmond and Savannah, and so actually I never went to the same school 2 years in a row. I was always kind of going back and forth and kind of missing a few grades, and so I don't really have a lot of sympathy for people that say, well, I can't move because my kids are in high school or something, you know. Well, get used to it.
What were your earliest mathematical memories?
The earliest kind of real mathematical memory I have was Miss Smith in the 5th grade in Berkeley, actually. And they used to teach ways for extracting the square root. There's like long division, but more complicated. And I came up with a way that I thought worked for cube roots. And I tried to explain it to her, and she was very interested, but I don't know if she understood or if it even really worked. But then the real kind of awakening, I was in the 7th grade, junior high school, and it was an algebra class, and the teacher saw that I looked not very interested at the back of the class, so he said, well, what's wrong? I said, well, I know how to do these problems. He said, well, okay, I'll give you a problem that I bet you can't do. It involved a population of mice which grew in proportion to how many mice there were. So it involved kind of a differential equation. Well, he was right. I couldn't do that. But he gave me a book, a calculus book. Actually, I remember it well, Granville, Smith, and Longley. And he said, read this book, and at the end of it, you'll be able to do it. And I did, and I could. So that was Mr. Schwab. He was also the chess coach. So I was on the chess team. And so that was my first real inkling. Of course, I always liked astronomy. I still like astronomy. It's amazing. But I think astronomers don't really look at stars anymore. They're sitting in their offices, and the telescopes are in Chile or Hawaii or someplace.
So what about high school experiences?
In fact, I didn't finish high school. I was in the 11th grade down in Florida at the time, and they had just put in the 12th grade. It was felt before that, well, why waste an extra year in high school? You could be out working. But the Ford Foundation had a program to allow you to go to university before you were drafted. And so I was 15, took tests, and I got admitted at the University of Chicago. And it was quite a eye-opening experience, for sure. Of course, at Chicago, the Great Books Plan, kind of pioneered by Robert Maynard Hutchins, great educational philosopher, that you should be well-rounded. And at Chicago, they give you tests in the college on 14 different subjects, and physics and math and biology and chemistry. If you do well enough in certain subjects, you don't take those. So I did well enough in physics and math, but I needed a little more French literature and philosophy. So I spent 3 years doing French literature and philosophy and trampoline and juggling. That was important too.
Did you take any math classes at the University of Chicago?
No math classes, no.
And tell me a little bit about getting into trampolining and juggling.
Well, bouncing around the high schools in Georgia and Florida and California, kind of the...
No pun intended.
But well, the jocks on the football team and so forth, these were the kind of the big men on campus. But I was younger and smaller, and in fact I was still growing when I was 19 or 20. And so I didn't do any of that. But at Chicago, they had a group called acro theater, which is a combination of kind of circus and gymnastics, and you took classes, and gymnastics was great because you don't have to be so big and strong. In fact, it's kind of a disadvantage. And I got into trampoline and juggling, and the rest is history.
So how many balls could you juggle at that time?
I performed with 6. And 7, I never really could make 7 go kind of in a continuous fashion. You play with it a little bit. Of course, like every activity, the level has gone up. Things that seemed kind of impossible 20 or 30 years ago now, 7 is the new 5, as they say in juggling, you see. I mean, 5 balls, if you do 5 balls, you've put some time in. 7, you've put in too much time. Anyway, people would often rather see juggling 3 torches or 4 hatchets than 9 balls. And so it's the showmanship. So I once had a conversation with Francis Brunn, who was a legendary juggler, considered at the time kind of the greatest juggler and of his generation. And I asked him, well, who's the best juggler? He said, well, it's easy. Who's making the most money? Well, that's kind of a pretty hard-nosed metric, but that's one measure. But there are some of the best technical jugglers are actually amateurs, because it doesn't pay to work, to kill yourself to learn some impossible trick that very few people could appreciate except another juggler. Juggling is often a very social sport, and you end up taking clubs that look, harder than balls. They're a little bigger, they're flashier, and you pass them back and forth to people, and you have big groups, and you can, and mathematicians, and a lot of the jugglers are mathematicians or computer scientists, have patterns, say, on every prime number throw, do something. Well, you're computing like mad and juggling, and it's a real kind of a mental as well as a physical challenge.
If you could go back to your early life and change or augment one aspect of your mathematical education, what would it be?
So what happened at Chicago after 3 years, didn't take any mathematics. I really wanted to study science, so I decided to go to Berkeley, where I kind of had grown up more or less. And I enrolled as a double E major, and I took number theory classes there. So actually from D.H. Lamer, who turned out to be my advisor. But after that 4th year, I still hadn't accrued enough credits to actually have a degree. And in those days, if you, after 4 years undergraduate, no degree, you can be drafted. So I thought, well, okay, maybe instead of being drafted, I could do something else. I could enlist. And I looked at the brochures. Army, 2 years, doesn't look good. Navy, 3 years. Air Force, 4 years. Oh, travel the world, get the duty assignment you want, everything. So I enlisted. And turns out that there was a well-known that I was, if you're sent to a technical training school and you do best in your school, in your class, you can get any assignment you want. So I studied like crazy and could type like mad and so forth, and was best in my class and got sent to Alaska with 4 other people, because it turns out in the real world, where you get sent depends on knowing the guy in the headquarters division that makes the assignments. That's how you really decide. So I was up in Alaska for 3 years, And I volunteered to work at night, and the days were my own, so I was a full-time student at University of Alaska. Got a physics undergraduate degree. They weren't accredited in mathematics, and so that was, but that was a detour that maybe in another life I might not have taken. I might have gone straight to university.
Did Lamer express any opinions about going to Alaska and enlisting?
No, because he didn't know. I was just an undergraduate. I disappeared. And while I was there, I met Donald Coxeter from Toronto, who was visiting, and he offered me a TA-ship at Toronto, which I didn't take. But then I came back to Berkeley as a grad student and worked with Lamer. Lamer was kind of a catch-all advisor. If you're doing algebraic topology, you do Spanier, or algebra, you do Rosenlicht or something. Logic, you do Tarski. But I was just doing kind of combinatorial number theory type things, and that was what Lamer liked. So I worked with him, but I never took a course from him as a graduate student, and should have learned more, could have learned more.
How long did you take before you switched from EE to math?
Well, I was never in E. I just had to pick something, you see. So I took mechanical drawing. I learned how to draw lines with arrows. Really good. I can draw very good arrows, yeah. But I took Russian, I took, all that kind of stuff. But, when I was graduating, it kind of never occurred to me that I'd have to get a job, because I'd always been in school all the time. I thought school was great, so I only applied to 2 places, Bell Labs and IBM. And that kind of disappointed Lamer. He thought, students should be professors, right? Well, what was I going to do? And I know I had a friend who was at Berkeley at the time, Harley Flanders, who said, you go to industry, you'll be dead in 3 years. Well, okay, I think he was wrong. In fact, he's dead, right? But anyway.
And what were your interactions with Lamer like? I mean, he's certainly an interesting...
Well, Lamer was an interesting guy. He has a very wry sense of humor. And I just learned relatively recently that during the McCarthy era, people at the University of California, faculty, had to sign loyalty oaths, or at least they were supposed to. And Lamer decided he didn't want to. So he was released. And then that kind of blew over. He came back and became the chair of the department, actually. And in fact, it turns out his father, D.N. Lamer, was also at Berkeley and was the chair of the department in the 30s. In fact, D.N. Lamer published the first kind of correct list of prime numbers up to 10 million. And people pointed out it wasn't quite error-free. He made one mistake. He included 1 as a prime, which nowadays people usually don't think it's a prime. But Lamer was very computationally oriented, one of the early people. For example, in one of the qualifying exams, when he asked a student, suppose you have 100 equations and 100 unknowns, linear, how would you solve it? And the student said, well, set up determinants. And Lamer said, have you ever tried to evaluate a 100 by 100 determinant? And the student said, I'm not interested in that question.
And what was your thesis on?
The thesis had to do with something that was more or less written when I was an undergraduate. So when I was an undergraduate, he had a letter from Sherman Stein at Davis. And there's a problem about decomposing fractions into sums of unit fractions, so-called Egyptian fractions. And you'd like to know, well, Fibonacci in 1202 proved you could always decompose a positive rational to a sum of distinct unit fractions. And the question is, suppose your initial fraction had an odd denominator. Can you then do the same thing with all the unit fractions with odd denominators? Well, yes, it turns out you can. Or suppose you want all the denominators to be perfect squares. Can you do it? Well, you can do it if you have a chance. Chance means if you take the sums of the reciprocals of all the squares, you get pi squared over 6. This is Euler's great discovery. So you can't have any rational bigger than pi squared over 6. On the other hand, it can't be negative. Well, could you get everything in between? Well, almost. If you use 1 over 1, it's got to be at least as big as 1. If you don't use 1 over 1, which is 1 squared, it can be at most 0.6 something, which is pi squared over 6 minus 1. So there's a missing gap. Other than that, any rational, you can actually do it. And in fact, I wrote this to Paul Erdős at the advice of Lamer, and he wrote back in 59. And this kind of began our first interaction with Paul Erdős, of which I have a long history.
So when did you first actually meet him?
I first met him in 1963. There was a meeting in Boulder, number theory meeting. In fact, at that meeting also, Helmut Hasse was there, which was kind of controversial because there were still a lot of people who felt that he was in Germany during the Nazis, and so there was some concern about that. But Erdös was there. It was my first real meeting. I got to meet him, and then we didn't start working until 3 or 4 years after that. And of course, Erdös traveled around like crazy, and he always needed a place to stay. And often he would give a talk at a school, and they would process the paperwork and send him a check 2 weeks later. But by then he's 3 places, so they never caught up with him. So he said, "Why don't you just kind of collect those and keep track of them?" And so I ended up kind of becoming his banker.
So that seemed like that happened fairly early on. Why did he choose you?
Well, I was kind of in New Jersey, which was one of his main stops, and I had a place he could stay. We fixed up an Erdös room. He needed his own bathroom, a telephone, and access to the refrigerator. And so we had all those things. In those days, Erdös was one of the few people who could still go in and out of Hungary. And a lot of the people couldn't, or when they did, like Lovas and Semredi and so forth, they would earn money outside, but they couldn't bring it back to Hungary. So it was kind of outside. And so Erdös would kind of send money from A to B and B to C. And so I have a big flow chart of which money goes where and so forth. So Erdös was kind of a central node there, and then I kind of managed the process. Erdös liked to offer small prizes for mathematical problems, and if it's a more serious problem, we got a bigger prize, or if it's an older problem, it's clearly harder. He offered kind of rashly, he said, $10,000 for a problem about the gaps, the large gaps between consecutive primes. And he said it was kind of a rash offer, but it's now recently been solved. And so I'm kind of on the hook. I didn't promise to do that one, but this was, James Maynard, and he did independently Terry Tao and Ben Green and Kevin Ford. And
So does the account with the money, did it have enough to pay
it does, yeah. He left some money just in case of this emergency. Now, he also wrote some checks. You'd have his check signed by Erdös, suitable for framing, we like to say, but often people cashed them anyway. But I think I ran out of those. So,
Tell me more about the Maynard Green solution. How will the money be allocated?
Maynard also was involved with the small gaps, which is the Zhang Yitang, and so he's clearly a very bright guy. And so I talked to Maynard. I said, "Look, you did it independently with Green and Tao and so forth, so I'll give you half, and the other half I'll give to the other team." And I talked to Terry Tao about it, and Terry said, "Well, I don't really need the money. In fact, there's a new bound on the gap between consecutive primes that has an extra triple log factor with a constant." And Terry said, I'm going to offer $10,000 if anybody can prove that constant goes to infinity. So Erdös had quite a few problems in combinatorics and graph theory. And so Chung and I wrote a book collecting these problems called Erdös on Graphs, his legacy of unsolved problems. And it's been out more than 10 years now, and we've paid off on 2 of the hundreds of. So they're not so easy.
So Erdös was always something of an eccentric figure, even among mathematicians. Did you have a feeling that you understood how his mind worked?
People often have the impression that all he cared about was mathematics, but actually cared about people, cared about politics, cared about a lot of things. Music, as he called noise, and he had his own language. So for example, men were slaves and women were bosses, and children were epsilons. In mathematics, epsilon also means a small quantity. So there was once a dinner with someone who knew his language and asked Paul, "Well, what would you like to eat?" "Well, I'll just have an epsilon." She said, "You cannibal," because she was using the other. Yes. Paul, he had visions, I think, that only he saw. Often he'd put out a problem that looks, doable, but you'd have to do something. You have to stand on your tiptoes to be able to do it. And once you could do that, you say, well, now you can do that. Maybe you can do this next thing. But I think he had in the back of his mind a bigger view of where things are going. because so many of his kind of harmless-looking problems, I mean, even somebody likes to think he worked on areas, just goofy problems, you see, but then they grew into something much larger. He was it's been almost 20 years since he died. And he loved to collaborate. I mean, he was the ultimate collaborator. He has, 400 collaborators and 1,500 papers, and he's working simultaneously. The thing he liked a lot, he valued a lot, were his mathematical diaries. And he would keep a pretty careful record every day what he was thinking about. And right now they're still in Hungary and they're not kind of available, which is kind of a shame. But he would often, when he's visiting someplace, he would come up to the person he hasn't seen for, say, 2 years and say, you know that graph problem that we looked at? Well, I think if you do this. Well, somebody said, what an amazing memory. I mean, no, the night before he was reading the diary to see what he talked about 2 years ago.
Now, did you come up with the idea of the Erdös number, the number of people connecting themselves to Erdös?
No, it wasn't my idea. I'm not sure whose. I don't think it was Paul's idea either. But he often would, he had so many collaborators, he had it was natural to say, well, suppose you make a graph, which is a set of people, and put an edge between them, a connection if they have a common paper, and now what's the structure of this big, giant graph? And is it a non-planar graph, for example? Actually, Berlekamp wrote a paper which would complete an edge to make it non-planar. That was the purpose of the paper, but never got published, so it didn't happen. And it's very similar to what's called the Kevin Bacon number, where you look at people who are in movies, and you put an edge between them if they have had a common movie. And so you have the shortest path to Kevin Bacon is usually in the movie world, maybe 3 or might be 4. And now there's the Erdös Bacon number. You can put your Erdös number, how many steps to a paper with Erdös, and how many steps to a paper, a Bacon, add them up. And I think I have a 3, which is pretty small. But Erdös, for example, say, well, who among us has the most prestigious co-author? It always was Ernst Strauss, his good friend at UCLA, who had 2 papers with Einstein. He was Einstein's assistant at the Institute. So Strauss won that competition.
What was it like when you started at Bell Labs?
Well, Bell Labs was an amazing place, and maybe it'll never happen again. The story, basically, AT&T was a regulated monopoly. I mean, it had all the telephone service in the United States, and if it needed to raise a little money, it just raised the rates in some states by 0.1%. And during the war, Bell Labs did work. They didn't want to do a lot of kind of military work, but if they had capabilities that other people didn't have, like detecting submarines or developing radar, things like that, they would do that. And so they developed a very high level of people like Claude Shannon was their information theory, people who invented lasers, the transistors, Shockley and Bardeen and people like that. And so when I went there, they told me, look, what you're working on might not be relevant for 10 or 20 years, but that's fine. We'll be here then, and we'll use it then. Nowadays, 3 years is pretty far down the future. And it was in a certain sense kind of an ivory tower in that you didn't have to apply for grants, you didn't have to teach, although I did teach now and then, and you just have colleagues, and there's very much an open door policy. You had physicists and chemists and even people in biology and EE and who love to talk to mathematicians. Of course, typically they have their problem, they come in and they mathematize it, and of course they really threw away the real problem, and you say, well, can't you do this? And they say, well, but of course, for example, when you look at lasers, you have a certain medium where the light beam goes back and forth, picking up energy, and then you let it out. And it turns out to be a problem in packing circles in a disk. You'd like to pack them very efficiently. And so you can do some mathematics and find, oh, this is really a great packing. and they actually build it, and you could see it. The trouble was, for this thing, it was in the infrared, so you couldn't really see anything, but you knew that it worked. And it was a great source for lots of problems that kind of came up, because the real world is a great poser of problems. I mean, if something's out there working in the real world, then something's working. So, okay, why is it working? Could you make it work better? And what are the alternatives? And so forth.
But you gradually ascended the management chain. When I met you, you had the whole the mathematics.
They had a policy in the research part that you'll be a better leader if people respect you technically. So they always tried to promote the people that were technically the strongest. These always, turns out, weren't the best people, because typically, it's a thing that was attributed to Andy Gleason, for example, at Harvard. Really super smart guy. When someone would come in, a possible student, and say, here's a problem, Gleason would try to solve it. Well, that isn't the idea. The idea is to kind of encourage the student. So one of the things they taught you there is called kind of non-directive counseling. Someone comes in and they say, well, here's a math problem. I say, well, okay, tell me about it. But then after 20 minutes, they talk about what was really on their mind. And so you kind of do that. But it was, the idea was to try to create an environment that's best possible for the people to do their work. It's hard to expect that I would tell, Tarjan what the right kind of graph algorithm problem is to work on. He can figure it out. You get the best people and create a good environment and let them go, and now and then you get a home run. You get a transistor, you get a laser, you get Unix, and most of the time you don't. But the ones that do pay for all the ones that don't. And then little by little, the Justice Department broke up AT&T, so the manufacturing part went off separately, and so a lot of the physics people left, and then Lucent came in and got split again, and now I was just there last week actually, and it's really kind of a shadow of what it used to be. So Bell Labs was a special place, and nowadays you say, well, there's anything like it? Well, IBM still has something. It's not, it's not as stellar as it used to be in many people's opinion. You have Google, Microsoft, but you don't hear much about the Apple research labs or the Facebook research labs. So there's a much faster turnaround, and long-term, 5 years is pretty long-term nowadays. People are worried about the bottom line, the quarterly earnings report. You don't have a chance to do something and say, well, maybe I'll use it in 10 or 20 years.
Do you think the labs are more secretive now for patent reasons?
I think so, yeah. If you go to Google, you sign a pretty strict non-disclosure agreement when you go in, and things are accelerating. And the next generation is maybe 2 years away and not 10 years away. The old Western Electric, which is part of the manufacturing at Bell Labs, they wanted to build something that would last for 40 years. Well, nothing lasts for 40 years. In fact, my PC doesn't last for 2 years. I think it's just the way things are going, and you have to adapt.
Did you start corresponding with Martin Gardner during your early time at Bell Labs?
Yeah, pretty early. Martin used to live in New York, Hastings-on-Hudson, and he loved to correspond with people who would write in with solutions to some of his puzzles. So I communicated with him that way, and I got to visit him. I remember once I was there and Roger Penrose was there, and Penrose had in his pocket these little carved wooden pieces that looked like darts and kites. And he said, Martin, this is kind of a funny thing. And I actually have one of the original darts and kites, these little quadrilaterals that tile but only non-periodically. Martin and I, and with my wife, Fan, actually wrote a paper on kind of the Steiner problem on chessboards. And it got an expository award. And everybody said, well, Martin Gardner, of course. You say, no, Fan wrote the paper. Martin said, I loved it. I didn't change a word. So whenever I'm having a discussion with a fan about a certain wording, she said, well, look, Martin. So Martin was was just an amazing guy. He felt that one of his big advantages is that he wasn't a mathematician. And therefore, if he could get it to the level that he could understand, then most of the readers probably could too.
So what was Martin Gardner like as a person?
He was very generous, and he often responded to correspondence with kind of handwritten, typed thing. He was very careful when somebody contributed to a column, he'd put their name. A lot of people like to see their name. So we went to visit him fairly often. Then he moved to North Carolina, and we visited him there. In fact, he had a lot of books downstairs, all the reprints of translations of his books. And in going downstairs, the stairs were uneven, and Fan tripped and split open her eyelid and had to get some stitches. And so that was a memorable thing for Martin. Then later, he tried to get a driver's license in North Carolina, but they wouldn't give it to him. He was a little bit old. So he moved to Norman, Oklahoma, where his son was at the university, in kind of assisted living. And Persi and I went down to visit him shortly before he died. It was slightly depressing, but Martin had then discovered the internet. And he said, wow, there's so much information out there. It's amazing. So he was still busy, kind of poking around. And we have some nice pictures of kind of the last visit. And so Persi and I and John Conway each had one of his books dedicated to us. So that was kind of the height of our interaction. But Martin was just great to talk to, loved to chat, and was always excited about some new, interesting mathematical puzzle. And he was kind of one of a kind, one of a kind. And, but aren't we all?
So when in this time did you meet Persi Diaconis?
Persi came and spent a year at Bell Labs early in his career, and we started working. Many of his problems are kind of combinatorial, number theory, probability, and we hit it off pretty well. And of course, he knew Martin from the old days. And then Persi kind of went off to Harvard and Stanford and Cornell and this and that. And many of the tricks in magic are based on mathematics. And Persi always was fascinated in just what the mathematics was and how you could extend that mathematics to more complicated situations and maybe make better tricks. And that was the theme of a book that we came out a couple of years ago called Magical Mathematics. Exactly taking certain standard tricks, or maybe not so standard, looking at the math behind them, and then seeing how that fit into the larger mathematical picture, and then seeing what new tricks could come out of that.
Were you interested in magic before you knew Martin Gardner or Persi Diaconis?
Not especially. I mean, I picked up a few kind of magic tricks along the way, but I was really more into juggling and things of that type. I mean, that juggling, mathematics is often called the science of patterns. And you can think of juggling as the art of controlling patterns in time and space. And, in juggling, one of the sayings is that the problem with juggling is the balls go just where you throw them, not where you wish they would go or you hope they would go. And there's a similar saying in computing. The problem with computing is that the computer does exactly what you tell it. There's no instruction that says, well, you know what I mean. And so you have kind of the ultimate control. So that's why a lot of jugglers are in mathematics and computer science, and not so many are in history or philosophy or art. It just seems to be a certain mental, in mathematics, there are always more unsolved problems. And in juggling, you never juggle all the possible patterns. There's always one more ball, or do it, in reverse.
In the middle 80s, kind of a systematization of juggling patterns emerged under the name Siteswaps. Why did it take so long for that to emerge? In retrospect, it's one of those things that seems very natural.
The idea of Siteswaps is a way to associate with a sequence of numbers certain juggling patterns. And typically a number says how long it's in the air. So a 3, 4, 5 says the first ball is in the air 3 ticks of the clock, and then the next throw is 4, the next is 5. and you could try to repeat that, and you could try to juggle it. And with that background, there's a beautiful theory that you can kind of develop, wondering about all the possible patterns. How many are there? What if you pass between two people? What if you could throw more balls than one from a hand? And it's just it's a very rich field in which you can apply mathematics. But then I think that's kind of true in anything. I spent a lot of time on the trampoline. Trampoline, you're juggling. You're the object. Don't drop, right? If you take a complicated skill, you break it down into component parts, you work on each part, put it together, and then you have it. For example, if you do a double back somersault with a double twist, you can't just say, well, I think I'll try it, see what happens. It won't work. You say, well, first you got to have a nice double somersault, but have a somersault before that, and then how about a full twist? And then, so I have a big trampoline outside with a big bungee cord, so you can't really get killed, which is good these days. Yeah.
You've got so many papers in so many areas that it's a little hard maybe for somebody to kind of stand back and say, what are the big themes? What would you say are the biggest themes?
Some of the themes early on came from problems at Bell Labs, for example. So early on in the kind of middle 60s, I was doing a certain amount in scheduling theory. Scheduling theory, you have a certain number of jobs, a certain number of machines, and each job has a certain amount of time and certain requirements that it must be done before others can be finished or started. And the question is that Bell Labs in those days was one of the software contractors for the ABM, the anti-ballistic missile system. And when you have a fleet of incoming missiles, you have to decide fairly quickly on what to do about it. Whose are they? Where are they headed? How should I respond? And they had programs, and they noticed that if they changed the order that they tried to do something, it would finish sooner than other times. It depends on the list. The question is, how bad could that variation be? And it turns out that kind of examining that problem, you can then come up with the idea of saying, well, it might be very hard to get the best possible list. In fact, it's known nowadays to be NP hard to do it. But you could say at least how this algorithm comes within a certain guaranteed factor, like at most 50% worse or 2/3 worse. And this was kind of worst case analysis, one of the first examples. It's kind of a big area in approximation algorithms to try to decide, sure, you can't get the optimum, but here's an algorithm that's not too bad, and you come within 10%. Maybe 10% is fine, you see. Then later on, I ran into people who are working on Ramsey's theorem. Now, Ramsey's theorem is basically based on the philosophy that if you have a large, complicated structure, then within that structure, there often, inevitably, is some more well-defined substructure. I think in the movie A Beautiful Mind, Russell Crowe, playing John Nass, points up to the stars and say, look at a pattern, look at a square, look at up there, and oh, look at this, almost a square. Well, Ramsey theory kind of makes that very precise, and it's been a very active field now. And of course, I and Bruce Rothschild and a guy named Klaus Leib at Berkeley proved kind of a very general Ramsey theorem that kind of implied kind of most all the known ones at that time. And then people wonder, well, the canonical example is the theorem of Van der Waard in 1927, that if you take the integers and you color them in two colors, one of the colors must have arbitrarily long arithmetic progressions. And the question is, if you have more colors, is it true? Or if you just have a bounded number, how many do you need before you're guaranteed to have a k-term progression? And that's been the thrust and the motivation for a lot of very recent work of Terry Tao and Gowers and Ben Green and people like that to try to get precise estimates on how fast these functions grow. very big thrust now in algorithms and a lot of areas of mathematics is the role of probability. You take a random graph and you say, what are the properties you expect of a random graph? Almost all of them have certain properties, and sometimes, Shannon was kind of one of the early people. Almost all codes are pretty good, but now find me a good one. Well, anytime you have a very specific rule, that's so special, that's not a random one, and probably it's not very good. So the idea that you could find very special constructions so graphs behave like random graphs, but they're not random. We termed it quasi-random. And so it turns out that there are a few conditions on a graph that once it has these conditions, especially for families of graphs, then in fact it behaves very much like random graphs in many other ways. There's a whole equivalence class of conditions. So this is also kind of an active area to decide how much randomness you need locally before the whole thing behaves globally like a random object.
The idea of quasi-randomness or the probabilistic method in combinatorics seem like the kind of things that are so obvious now they should have been discovered earlier.
Right, like the safety pin, right, or the paperclip.
Right.
Why didn't I invent that? Right. Hindsight is great, and it's you never know. When you plant a seed, a little acorn, will it just turn into a weed, or will it be a great oak tree? You don't know.
It seems like combinatorics and discrete mathematics have had that happen a lot.
Well,
over your career.
Yeah, combinatorics is a relatively recent, has recently emerged and kind of a little more mainstream. And in the old days, graph theory was often called the slums of topology. And Erdös Number he wrote about kind of the panorama of mathematics. In the French version, combinatorics was called breakfast mathematics. In the English version, it was pre-mainstream. But now it turns out that there's a more of a well-defined body of tools, the regularity lemma and the Graph-Minor's theorem, really substantial theorems, which can be applied in general situations. For example, Semiretti's regularity lemma now is a key part of the Green-Tau theorem that the primes have arbitrary long progressions. And people begin to understand and use some of these more powerful techniques. And of course, the computer is big. A computer is basically digital, and you got zeros and ones. Then you have integers, and if you have integers, you have number theory. And so it's really, it's a very natural thing to emerge. I wrote a book with Don Knuth and our TA, Oren Patashny, called Concrete Mathematics. And the word concrete came from continuous and discrete, the two words, to show that the interplay between the continuous and the discrete. So I think early on differential equations were continuous, and now the pendulum is swimming a little more toward the discrete end and the interplay back and forth. So I think when you get Fields medalists in discrete mathematics, combinatorics, that gives it a certain okayness, right? It's okay, right?
Where do you see combinatorics going in the near future?
It's a complicated question. For example, Tim Gowers, that people respect a lot, feels that by the end of the century, mathematics will be done mostly by computers. They'll make the conjectures, they'll have the proofs, and our job is to kind of tag along and see how to apply it. There's a nice story that you ask in 100 years, oh, great computer, tell me, is the Riemann hypothesis true? The computer says, okay, come back after lunch. You come back after lunch, and he says, well, yes, it's true, but there's no way you could understand the proof. Well, okay, if that's the way it is. There's a certain philosophical point of view that, and there's a little more evidence to the truth of this, that most mathematical statements are kind of beyond proof of human being in the following sense. Look at one of the more recent accomplishments, say the classification of finite simple groups. You can state the problem on a page. Could you ever find a proof in 100 pages, 1,000 pages? I don't know. I mean, for example, the four-color theorem, which is a theorem about coloring maps, recently proved by computer, billions of cases. And one of the provers, Wolfgang Haken, feels there won't be any short proof. It's true because 100 billion things are true. That's the reason. Well, how would you, if that's true, no human being has ever checked that proof. Well, do you believe it? Well, if your computer program is correct, well, you can check that. If that's the case, and there are fragments of mathematics in which there are statements that are true statements in that fragment, but the shortest proofs there are doubly exponential. So you won't really be able to find a proof. I mean, there's kind of not a real conjecture in number theory. To prove that a number n is prime is going to take a number of steps that grows at least like the logarithm of n, which is kind of Mersenne prime. And now if that's true, then you have a number like 10 to the 10 to the 10 plus 73. If it's prime, you'd never be able to prove that it's prime. You can give these probabilistic tests, and it looks like it's behaving like a prime, but you never prove it. So the whole edifice is kind of shaky if you can't really prove it. And then, there's a question in mathematics, what's more important, something coming up with a conjecture or the proof? I mean, sometimes if you know what you're trying to prove, sometimes that's half the battle. You often don't know. When they tried to prove this conjecture of Euler, that you couldn't have a fourth power of an integer, the sum of 3/4 powers. And people tried like crazy to prove that for a while. And the reason they got stuck and they couldn't prove it, it wasn't true. And that often slows people down, although not everybody. And in fact, that was, the theory there. And then the Nomelkes finally found examples and so forth and so on. But it's just a message that when you're trying to prove something, you're kind of convinced it's going one way, but it's really going the other way. So I have a saying I always keep in mind. The main obstacle to progress is not ignorance, but the illusion of knowledge. You think you know. No. Once you understand you don't know, then your mind is a little more open to say, oh, okay, there are other possibilities. Like maybe it's not true after all, even though you wanted it to be true.
What questions would you like to solve or hope to see solved?
I have a friend who is a mathematician friend who had 2 steps to immortality. Okay, good. What was that? 1, identify a problem that you love so much you take a solemn oath. You will not die until you solve that problem. Step 2, never work on that problem. The trouble is somebody else may solve it, you see. There are a lot of problems that are in that category for me. Maybe I don't say I'm going to not die until but they're very frustrating. One of this is the growth of the van der Waals function. That is, the finite form of this function says, say for 2 colors, that there is some number, W of k, depending on k, that if you color the first W of k positive integers, red or blue, then you must have either a red or blue k-term progression. The question is, how small can WK be? And I actually lost $1,000 to Gowers because I had a conjecture that W of k is no more than 2 to the 2 to the 2, a tower of 2s of height k, and which is a pretty big number. However, he showed that it's actually less than 2 to the 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 k plus 9. Well, he said, for a k equals 6, it probably still is. I said, look, that's fine. That's $1,000. It's good. I have another conjecture. It's no more than 2 to the k squared. And that's completely out of reach. So I've been thinking about that in various versions. And, Hilbert said it. I kind of ascribed to his philosophy. We must know, we will know. Okay? Now, who we is another story, but humans, we must know the answer. We will know someday. But, the Riemann hypothesis, the Hodge conjecture, everything, P versus NP. And this is kind of the number one problem on a list of what used to be 7 $1 million problems from the Clay Mathematics Foundation. Now there are 6, given the Poincaré conjecture is settled. And most people believe that P is not equal to NP. That is, there are certain problems that you cannot solve efficiently in general in less than exponential time. But there's some people who feel maybe that's not true. It's just that as human beings, we are just not capable of really understanding the very complex polynomial time algorithms, that might have, k to the 100,000th power. I mean, just, practically, algorithms not very useful, but, the theory. So it's hard to know. I mean, some of the recent movies show, like Her, guy falls in love with an operating system, or Ex Machina, where a robot really passes the Turing test. I don't want to be a spoiler, but so I think machines have a long way to go, and it'd be interesting to come back in 100 years and see whether mathematicians are like librarians, they just kind of keep track of stuff, or whether they're still on the forefront.
You've given us two visions of progress. One is bright mathematicians doing interesting new things, coming up with new ideas. The other is computers taking over. Do you have a feeling of either which will happen or which you would want to happen?
There's always the next generation of smart people having new ideas, but computers are exponentially getting better and better. And I think I've seen examples long ago where you taught a computer how to learn how to play a game. And at first it was hopeless, but after it played itself 10,000 times, it started playing better than the humans. Well, chess, for example. I think computers now are better than humans at chess. And once computers learn how to learn, I think that there's a real issue as to, it's the kind of Terminator situation, right? I think computers, I think there are people who are really concerned that, you get very intelligent machines that they don't want to let you turn them off, right? And so I think it'll take a while. And they say that's one difficult thing about the future. It's hard to predict. Right? So, well, we'll see. Or some of us will see, right?
Among those mathematicians that have some talent at leading, at managing, you've been the president of the American Math Society, the Math Association, the International Juggling Association. You've been involved in boards and activities for the National Academy, AAAS, many, many other organizations. What enables you to do that so broadly?
One of the key aspects of good management is to delegate. And you delegate responsibilities to people, and you let them do their job. I mean, there are some people who care so much that unless you're doing it their way, that's not the right way. And that really frustrates people below them. So find people, especially find people who would like your job, and let them prove how well they can do pieces of it. One might think that the president of the Math Society or MA has a lot of clout. They don't really. They don't really as much. It's a little bit like you think the president has a lot of clout. Well, Congress, also can make it difficult for him. But I think one of the main aspects of good leadership and for the math societies is to identify people who will arise to the next generation of leadership. So you appoint people on committees who then become more visible and end up on the council and executive committee and emerge into the leadership position. So that's, I think, is an important aspect to being a leader, namely finding ways for people to come up and they can also become leaders. And so that was always my philosophy. Bell Labs, it was always kind of the three levels. First, best for the person, then best for the profession, and then best for the company. But I always felt what's ever best for the person, that's the dominant theme for me.
I was struck at the birthday conference a few weeks ago for you that so many of the speakers, it's not just they thanked you for talking to them and collaboration in many cases, but they were genuinely grateful for you having played a role at some critical point in their career in terms of giving them advice, which turned out to be prescient. How do you decide who you talk to in that way, and how do you decide what to say to them?
Well, I like to help people, and especially at the beginning, you often can remind people that, this might be more effective in that way. And especially I've tried to help, for example, women in mathematics that are always feel like they're, haven't quite caught up yet. I mean, there's certainly many, many strong women, but for various reasons, they didn't quite make it into the upper echelon as quickly as you think they should. And so when I'm on committees, I try to, select a broad range of people and try to give, it's just common sense. And I kind of believe everybody is good at something, and you try to help them maximize that. And to the extent that people help you, you feel now it's your turn to help somebody, and you teach them that it's in their turn to help somebody. So it's a little bit like teaching juggling, and I'm sure you've done a lot. You teach people, and not only that, you teach them how to teach people, and then they teach, and it spreads exponentially. Why isn't everybody a juggler?
When did you first meet Van Chung?
So Bell Labs is in Murray Hill, New Jersey, and not far away from University of Pennsylvania, like an hour and a half away. And I knew her advisor at that time, Herb Wilf, and I would give talks at UPenn, and he said, I've got this terrific student working in Ramsey theory. Well, that's pretty natural. And I met her, and she came, gave a talk at Bell Labs, impressed everybody, so we made an offer, and she took it, and she was hired, and there she was, Bell Labs. So, we've written, she's a great collaborator, and, super strong. And we've written, I think, 90 or 100 papers maybe, and now she's kind of gone off into spectrograph theory, which is an area I don't work in so much, but it's just part of the collaborative activity at the labs where people would just work with each other in joint papers with, a tremendous number of people. I mean, Ligarius, Lisco, all these people, Gary, Johnson.
What other collaborators stand out in your mind from your career?
I've had a lot. I mean, I have papers with John Reardon. I mean, kind of a legend in combinatorics, right? And of course, with Erdös, we have 25 or 30 papers, something like that. He was a key player. Persi, you probably have 15 or 20 papers, and it's just that typically you solve a problem, but it's not completely solved. There's always a little more to do in the next case. And what about 3 dimensions? And what about hypergraphs? And what about the directed case? And so forth. And so, each solution generates 3 new problems typically, so you don't run out. And it's just that at the labs, that environment, you get exposed to so many different kinds of problems. Extremal graph theory problems and geometrical packing problems. Problem with Erdös we just worked on again recently. You take a square of side alpha and you want to pack as many unit squares that don't overlap as possible. How many can you get in? Well, if alpha is an integer, like 1,000, then you can have 1,000 squared, 1,000 by 1,000. But suppose alpha is, say, 1,000 plus 1 over 100, just a little bit more. Well, if you pack them in a nice orthogonal way, it's pretty good. You have a little waste area around the outside that's proportional to 1,000, proportional to alpha. So you wasted kind of a linear amount. Turns out by putting them in crazy angles, you can actually get the waste down to about alpha to the 7/11ths, about point, much better. And now is that the best? And now with a little more work, you can get it down and down. And then Roth and Von showed that you can't get it better than the square root of alpha. So what's the right answer? I don't think it's the square root, by the way. I think it's bigger. But so just little problems like that lead to kind of, harder and harder challenges. And as is said, problems worthy of attack prove their worth by fighting back. That's my variation of the Pete Hine classic. Yeah.
Did you ever interact with John Conway?
I used to see him fairly often during the summers. He was a very constant visitor of Neil Sloan when they were working on sphere packing and coding. And he would come up. He's a very interesting, unusual guy. If I had one word to describe him, I'd say he's surreal. Surreal. So he's interested in kind of physical things too. So I taught him how to take a hanger, and you can kind of stretch it so it makes kind of a square shape, and balance a penny on the end of it, and then spin it around, the penny doesn't fly off, and then stop it. And stopping is kind of the hard part. He really was fascinated by that, so he practiced like crazy, and he actually got pretty good at spinning it horizontally, which is harder. And I was into boomerangs at the time, so I was telling him how to throw a boomerang, and he started carving his own boomerangs. Now, he had a stroke not so long ago, and he said he couldn't do the penny on the hanger anymore. I said, well, try it with your left hand. He said, I tried. I couldn't do it. So it's kind of maybe it goes the opposite direction, right? No. If you say people are one of a kind, definitely Conway is one of a kind. He's a very interesting guy. We have one joint mathematical publication. So it was a problem in the American Math Monthly that kind of generalized one of these unusual nonlinear sequences. In particular, it's easy to explain. You take a sequence that xn depends on the previous two values. So xn plus 1 is equal to a fraction. On the top is 1 plus x sub n plus 1, and on the bottom x sub n. So that's how xn plus 2 is defined. And then you just start it and you see what happens. Well, it turns out amazingly it has a period 5. It's periodic with period 5. And we have a problem that generalizes that to something that has an arbitrary period bigger than 5. And what happens in the middle, it gets really complicated, and then it kind of amazingly simplifies. So that was our problem. That was the problem in the monthly.
What do you remember about Claude Shannon at Bell Labs or later?
Well, Shannon left Bell Labs in 1956. He never really came back much. He was employed as a consultant because he was also very interested and knowledgeable about the stock market. And so he would consult the economics people sometimes, but he never would come down. And I got to know him in his interest in juggling. He was very interested in juggling. He built some devices that simulated juggling. They didn't really throw the objects, although one did kind of bounce steel balls. And he was interested in manufacturing non-standard unicycles. I tried it. He had a unicycle with no seat, which you just he had one with no pedals. You have to sit on the seat and you push the wheel with your feet. And he had one, often jugglers, when they're juggling a unicycle, they want to rock back and forth in one position so they face the audience and they can do whatever they're doing. And if you do that, you kind of go up and down. But if you mount the wheel off center so that then it goes constant, you could be at a constant height. Of course, if you rode it, you would do it like that. And he built one unicycle. No two people ever managed to learn to ride, a unicycle for two. But and then someone broke in and stole his unicycle. So very strange, you see. But I tried to teach him juggling 5 balls. He could do 4, but he said it was a little too late. I think he was in his 70s, and I brought some orange lacrosse balls that are a little easier to see, but he didn't quite learn it. But he did design and build a rocket-propelled frisbee, and with 2 rocket sources, one for rotation and one for propulsion. And he had a little plaque on the wall from the Whammo Corporation citing the fact that he the first rocket-propelled frisbee. Well, okay, good. Claude was an interesting guy, yeah. He never wanted to talk about information theory.
Well, he had such seminal ideas, but it seemed like he really left them
Well,
behind.
he told me he was giving a talk once, and he didn't like to give talks that much, and he saw he was starting to lose the audience. He said they were just, so he had juggling balls. He started juggling. He brought them all back, and the talk was a great success. So that was one of the practical aspects of juggling.
What's given you the most satisfaction in your career?
Well, you always have a feeling of satisfaction when you struggle with a problem for a while and you finally see, amazing. You know, they say in mathematics, 95% of the time you're butting your head against the wall, and 5% you're kicking yourself for seeing why you didn't see that in the first place, you see. So it's nice to work on problems, and I like to work jointly with people. I mean, mathematics is in that sense a kind of a social activity where you bounce ideas back and forth. And the fact that you can help people. You know, the last 15 years or so I've been teaching a lot. And, you know, by and large, students are either very good or not so good or not so interested. But now and then you get one that really shines and you really say, they understand. And that's a feeling of accomplishment, to kind of pass on to the next generation your ideas. It could be juggling or mathematics or whatever you're doing. And that's, you know, I like to do that. That's fun. And you'd like to solve these unsolvable problems. I'm not working on the Riemann hypothesis, and Gauss didn't work on Fermat's last theorem.
You won't be surprised to know that many of your friends think of you as somebody who accepts all invitations, at least all that are sort of humanly possible to do. And for a lot of people, that would get in the way of research. For you, it just seems to heighten it.
You would like to think you get a lot of work done on the plane, but I think, in fact, you don't as much as you think. And I have to be kind of selective. I mean, but if there's an invitation that goes to kind of a new place, or you're kind of helping out someone, he's a new department chair and he wants to, you know, have a nice meeting and attract people, and well, okay, you do, it's interesting. And often you go to a meeting and it's easy to accept an invitation 2 years from now. You come to, you know, Tasmania, oh sure. Well, when that time comes, you say, wait a minute, I have to go to Tasmania? Is there some way I can? But when you go, it turns out typically you make connections you didn't expect, something good happens, and so overall it's usually a positive experience. But, you know, I definitely just got my 2 million mile mark on United, so that's probably says I'm traveling too much. We got to cut it back a little bit.
I know that you wrote a book with Persi, you mentioned, on mathematics and magic, but I seem to have dim recollections that it took a while to write it.
Well, in fact, the book you mentioned just happens to be right here, Magical Mathematics. Amazing, good. And what happened was that we had early on planned to write such a book and kind of knew what the chapters, and we got a contract with Princeton University Press that was due in 1986. Okay. Well, one thing led to this and that, and it's always more fun to kind of do new mathematics than kind of write up the old stuff. And we were still working. So finally, a few years ago, Percy's wife said, look, you guys, you get with it, because if you don't, it's just not going to happen. So, okay, I went up every 2 weeks, and I said, okay, Percy, let's do it. And we had one of the chapters, the 10 mathematical stars of magic. And but by the time we actually were writing them, all but 2 were dead. And Martin was the next to the last, and then he died. So there's still 1 left. And we only got 7, I think. And that's only about 2/3 of the book. We said, look, there's more we could put in, but if we don't stop now, it'll never. I think most books are actually started and not completed. And but I think there'll be a nice book on mathematical juggling coming up one of these days with you and a few co-authors. We'll see, but I hope it won't take us long. But as Gauss said, few but ripe, right? So this was definitely ripe.
Tell me about Graham's number.
Well, that's kind of a joke in a way. I mean, there was a combinatorial theorem whose proof used very kind of recursive multiple inductions. When that happens, you tend to get large numbers. And this was a problem, the following. You take an n-dimensional cube, already think about that, it has 2 to the n vertices. You join any 2 vertices with a line segment, so you have 2 to the n, choose 2 line segments. You color them red or blue, any way you like. The question is, can you always find 4 of the vertices so that all the 6 line segments have the same color, and these 4 points lie in a single plane? Normally, if you pick 4 points on a cube, 4 vertices, they'll span a 3-dimensional volume, but these are flat. Will it always happen, no matter how you color it? It said, yes, it will always happen if the dimension n is large enough. How large is large enough? Some really big number. Such a big number, you can't use ordinary notation. You need some arrow notation, just like the Ackermann function, only much, much worse. And the best lower bound when this happens seems to be 13, seems to be the right number. But this big number, it's kind of in Wikipedia. In fact, it was in the Guinness Book, the largest number that ever really occurred in mathematics. And it's just very large, that's all. And it seems the true answer to the problem might be 13 or 14, which just illustrates the gap between what seems to be true and what we can prove to be true. It's a pretty big gap. You'd like to close it down a little bit. So it's not really mathematics significant. It's just something that people can kind of mention, think about. Graham's number, what is that? It's a big number. How big is it? Well, it's so big that how many digits does it have? Well, about the same number. It's so big. You say, really? Yeah.
One tension that one sometimes sees in mathematics, or maybe dichotomy is a better word, is structure and explicit problems. So combinatorics has a lot of the latter and is gaining more of the former, some theory of the structures that arise. Do you see yourself anywhere in the pole of what you sort of like most?
Well, one of the themes coming out, and I guess in some sense the regularity lemma kind of typifies that, is that large structures often are composed of something that's pretty well structured, and what's left over is pretty random, and then there's a little noise at the end. And one of the themes in Ramsey theory is that complete disorder is impossible. And I heard a saying from a lawyer recently that says, complete disorder is inevitable if you have a lot of lawyers together. But it's a very nice idea that something looks really complicated, actually inside there's some very well-structured thing going on. And instead of that, something even more well-structured. And it's just that you don't see it. I mean, there's a nice example. There's a certain recurrence that says if you know xn, I'll tell you how to get xn plus 1. It's kind of a simple thing. And it turns out if you take this sequence, it's a sequence of zeros and ones. It just looks pretty random. It came up in some sorting algorithm. Somebody from the labs, well, can you say what's going on here? And you look at it. And it turns out that after you think about it for a while, look at it, I recognize the 1, 0, 1, 1, 0, 1, 0 as the binary expansion of the square root of 2. It was actually, now why I would recognize that, I don't know what I was thinking about. But once you see, oh, looks like that's what it is, not so hard to prove. So something that kind of looked random actually was very well structured. It's just that you didn't understand that until you... So I had this discussion with Steve Wolfram, who has this theme, the certain cellular automata certain rules for generating what happens at the next state given the local situation of the current state of each of these blocks on a big tape. He says, look, once it gets reasonably complicated, it's just kind of unpredictable. It's random. You'll know. I said, well, maybe it is a little more predictable. You just don't quite see what's going on.
It sounds like you're even really rejecting the dichotomy between concreteness and structure, namely they're both present.
So I always had the belief that somehow in mathematics, the probabilistic method is very powerful. And it says, look, you just look at all possible graphs, for example, where you flip a coin, put an edge in or not, and with very high probability, something happens, okay? And then you can use this argument to show something must happen, because the bad things, there's just not enough of them. But you don't know how to get a good thing. You can't actually construct a good thing. And I always felt that constructive methods are really, eventually will dominate. But now I'm not so sure. Not so sure, you know? Not so sure. I mean, the fact that we're humans is really pretty limiting, you know? I mean, we didn't evolve to understand the structure of the space-time continuum or view things 100,000 dimensions. Whereas we just want to, we know how to stay out of the rain and keep getting eaten by animals, but we're not really up to the job of, you know, the Riemann hypothesis or something. I mean, there's a story, there was a race so advanced that they awarded a prize to the first mathematician who actually realized that the Riemann hypothesis needed a proof. Isn't it just obvious? It's like the Jordan curve theorem. Well, I mean, you draw a simple closed curve in the plane. There's inside and outside, obviously, right? Well, not so easy to prove. Well, you know, a race so advanced that, you mean that needs a proof? Come on. Well, so, I don't know, I think we've got a long way to go. I hope we get there, you know, humans. But, I mean, the fact, back to astronomy, it looks now that most stars have planets. Seems to be the case. And our galaxy has about 100 billion stars. And there are about 100 billion galaxies that we know about. That's a lot of planets. Something's got to be going on. We're the only ones. As Carl Sagan, my classmate at Chicago, by the way, said, if so, it's an awful waste of space, right? Yeah.
When somebody gives you a problem, how do you work on it? I mean, how do you do mathematics?
So that happens pretty often, actually. I just got a nice problem from Don Knuth. It looks tough, actually. And sometimes you'd like to know the history. What partial results are available? What have people tried? And sometimes that's not a good idea, because once you see what people are trying and how they approach the problem, there's a tendency for you to fall in the same lines of thought. And if you did, well, that evidently didn't work. So I think it's a problem with composers. How do you compose a brand new melody, given that you know all the melodies that you've heard all your life? So often you try to put the problem in your own domain. This is a problem about certain structures, but if there's a numerical aspect, I can have numbers. And I like to get data. I like to say, look, the data will kind of suggest what might be true, what might not be true. Sometimes it'll fool you. Often you talk to people, and they have different ideas. You try to understand, but often you don't really understand until you convert it in your own language. And then you have to have a time where you just sit down and think about it. And I think it's very common in mathematics for someone to think very hard for a problem, about a problem for many days, weeks, go to sleep, and then you wake up and say, wow, I think I see what to do. Now, sometimes that doesn't work at all, but sometimes it's amazing. It works. That actually, why didn't I see that before? And so it's kind of an interplay. You got to think about it, focus, but then you bounce ideas back and forth with people. And, you know, I know some people who are very strong at particular things, like Richard Stong. He's amazing, amazing guy, right? So,
how do you balance needing to go in a corner and think and talking to other people to get ideas?
I mean, people with the internet now, people are constantly bombarding you with, what about this problem, this, and they're all kind of listservs that list big collections of problems, you know, and you could decide, oh, that's something kind of interesting, or I think I know about it, or I think it's already known. And can you find it in the literature? Well, that's another thing that the internet makes a little bit easier, but still, not completely easy. And you have to, I think you tend to tackle problems that are attractive to you, that are kind of aesthetic, that are nice, and then maybe you think you can do, you see? I mean, again, there are problems that are completely outside your area, or you're just not interested, and you're probably not going to do very well on those problems. And a lot of problems are the same problem in different guise, different language. You say, this looks like a problem about matrices. Well, really it's a problem about graphs. Well, actually it's a problem about sequences of numbers. Well, okay, so you move it into whatever domain you feel comfortable. You have some tools. And often there's kind of a difference. People who use the big machines, the tools, and there are a lot of tools, and people who just want to go out in the desert and I'm going to build my own tools because no tool will do the job for the problem I'm trying to solve. And once you build a new tool, like Andrew Wiles had to build some new tools, and once you have the new tools, you can then solve more problems. And Hilbert wrote a little essay on the role of problems in mathematics. He said, as soon as your branch runs out of problems, well, that's the beginning of the end. And the role of problems is to force you to create new tools to test the temper of your steel, to solve these problems. And once you have these tools, now you can attack harder problems, the next level. And and that's happened for Andrew Wiles, yeah. So it's kind of an interplay. It depends on your mood. And usually you're working on 2 or 3 problems at once. You get stuck on one problem, you go into another one. Or all the problems, well, I'll work on some juggling pattern that I didn't quite get yet. There's a nice story. At many meetings, there's a problem session. And typically the organizer likes to call on someone who has kind of a typical good problem, not the speaker who needed 20 more minutes to finish his talk. And so once Erdös was in the front row, kind of his head was down a little bit, and John Selfridge, who often was the kind of narrator at the problems, whispered in a kind of loud voice, "Paul, do you have a problem?" And Paul said, No, I'll be okay in a minute. So.
How does your Kevin Bacon number happen to be 3?
There's the strict Bacon number versus not so strict, Now, if you're in a documentary, sometimes they don't count that, you see. You have a speaking part, you see. And so I think through N is a number, where Alec Guinness is in that. And of course, once you're in Alec Guinness, he didn't have a speaking part either, but he was kind of marching along. I mean, he didn't look like Obi-Wan Kenobi, little guy. In fact, there's a story that the procession went along, and Alec Guinness was right behind Paul, and it made a turn, but Paul was kind of marching off his own way, and then Alec Guinness had to run out and get Paul and bring him back. And Paul said, I would have found it. It would have been okay. So once you get to Alec Guinness, I think right away you get to Kevin Bacon pretty soon, maybe even directly.
Are there any other memorable movies you've been in?
There was a BBC movie on infinity. The question, is Graham's number infinite? No. Is it pretty close? Well, no, it's an integer. It's pretty far away.
What about non-documentaries?
Well, there's a movie that's just coming out by Penn Jillette of the Penn and Teller Magic Trio. Penn's a pretty good juggler too, and he's making a movie. And I play in a flashback the role of Albert Fish, the oldest criminal ever executed at Sing Sing. He was kind of a child murderer and cannibal and kind of a bad guy. And it's a flashback, and I have to do various Albert Fish kind of things, but no speaking lines, just, and as Van says, it's so much made up they'll never know it's you, so it's okay.
But you're credited in the credits.
Yeah, credited.
So
yeah.
Those of us who are interested in your career can
see
check the movie out.
IMDb has categories. You're an actor, you're a writer, you're a producer, something like that. But there's no category mathematician. So I'm just actor, you see. So, yeah. Well, does this count? Does Science Labs count? No. Okay.